Well, section 14.1 is actually going to be quite easy. Level curves. The idea is you have something in 3 dimensions and you want to describe that in 2 dimensions like a piece of paper. Well, here's an example. A contour map. So you have this little mountainous region right here, and you want to take this information which lives in 3 dimensions and then be able to describe it in 2 dimensions like down here. So as you go along this line, you would be at an elevation of 1,200 feet. And if you do not go up the mountain or down the mountain, but just go around it, you'll always be at 1,200 feet. So that's what this line right here is saying. So this is a contour. And then in calculus, we call this a level curve because we're basically saying when you're at the level of 1,200 feet, then what does it look like? If you traverse the mountain around the outside, staying at the same elevation, you would follow this path 1,200 feet. And if you didn't know what the mountain looks like, you could see this area over here. It's going from 1,100 and it's not changing, and it's 1,100. So this area over here is not very hilly. This area right here would be the steepest because you're going from 1,100 to 1,200 to 1,300 to 1,400 in just this little span right here. So then you could see that this would be the steepest part because that would be when you're going right up here, the steepest part of the mountain. And this part was fairly flat. So that's this part right here. Okay, then on to some examples. So for example, suppose you have z equals x squared plus y squared. So what kind of shape would that make? But we're not looking at it in 3 dimensions. You notice that I don't have a graphing calculator or GeoGebra right now. I'm just doing this in 2 dimensions. So if I put z equal to 0, that would mean 0 equals x squared plus y squared. And that would mean that x and y have to equal 0. So that's just the origin. Then how about if z equals 1? So plug in z equals 1, and then you get a circle of radius 1. And then I'm going to skip to z equals 4 because then that's going to be a circle of radius 2. And then I'm going to skip to z equals 9 because that will be a circle of radius 3. And then you could do fancy things like label it. This is 3, 2, 1, and this is 0. You could even label it like this one is when z equals 0. This one is when z equals 1. This is z equals 2. And z equals 3. So this is actually used in a lot of different ways. For example, if you look at a map of the United States, here's a map of the United States. There we go. So that's in 2 dimensions. And then you might be looking at the outbreak of a virus or something like that. And then how fast is it spreading? So then you could have some type of graphic that shows in this area it's spreading quite rapidly, and then right here in Kansas there's only a few little dots. So mapping, you're able to convey information that has more than just 3 variables and get that information across to other people. All right, for the next example. So here's one that has more than 3 variables. Suppose that the function is a function of x, y, and z, and it equals x squared plus y squared plus z squared. So now this is in 4 dimensions. The only problem is that we live in 3 dimensions. So how can I graph 4 dimensions? Because this is basically like saying you have a new variable w, it equals x squared plus y squared plus z squared. What does that look like? Well, then do level curves. At the level where w equals 0, I know it's not going to be negative because all these are squared. So the smallest it could be is 0. That would be 0 equals x squared plus y squared plus z squared. And that would just be the origin, because it has to be 0 plus 0 plus 0. If w equals 1, it's going to be 1 equals x squared plus y squared plus z squared. And then that is a sphere of radius 1. If you let it equal 4, then that's going to be a sphere of radius 2. So even though this thing lives in 4 dimensions, then I can see what it looks like. It's basically like you're taking a snapshot at 0 seconds, 1 second, 4 seconds, and then you're seeing what it looks like. So it's a dot, and then it's a small sphere, and then a bigger sphere, and a bigger sphere. It's sort of like the Big Bang Theory. Everything starts as a dot, and then there's this huge explosion which goes out and out and out and keeps expanding and expanding. Then I looked at the homework and they word it like this. Sketch a typical level curve. And basically what they're saying is, you did this 3 times, which was nice, but you really just need to do it once. For a 4-dimensional function that is z minus 5x squared minus 5y squared. Okay, so a typical one, just pick a number. 3 sounds good. So you plug in a 3 right here. And then we need to graph this in 3 dimensions. So I'm going to take this negative 5x squared and this negative 5y squared and move them to the other side. And then what does that look like? And then of course you could use the GeoGebra to graph that. If it didn't have the plus 3, that would be a paraboloid. And because these 5s are the same, it's going to be a circular paraboloid. Then with the plus 3, that just means that z equals, the z was shifted up by 3. So shift up by 3, and then make a circular paraboloid. There you go. I could put another one of these things on it to make it look all fancy. And there is one typical level curve. So if this would have been a different number, like a 5, that means that it would have been shifted up by 5. So it'd be the same shape, except you would start it right here at 5 instead of here at 3. So it's basically just a bunch of these circular paraboloids going up the z-axis. Then for one more. So again, I was looking at the homework. So not only sketch a typical level curve and find the domain. And this one's going to be f of x comma y comma z is equal to z minus the natural log of x plus y minus 1. I think I'm going to do that part first, find the domain. Well, with the natural log function, whatever's in the argument, that needs to be a positive number. So that means x plus y minus 1 needs to be a positive number. Not equal to 0, but positive, bigger than 0. So this is now in 2 dimensions. It's only got x and y. So what I'm going to do is just move the 1 over and the x over. So this is in 2 dimensions, so I could graph that. Now it could be that they ask you to do it algebraically, and you would have this as your answer, or graphically, so then graph this. So this is a line that got shifted up by 1, and it's got a slope of -1. So that means it's going to go through 1 because it got shifted up by 1, and then 1. That way it has a slope of -1. Oh, actually this doesn't have equals. I should be making a dotted line right now. And then y bigger than means that the graph only exists over there. All right, that's the domain part. Now, what about a typical level curve? So you could just pick a number for this, like 1 equals z minus the natural log x plus y minus 1, or z equals, so take this natural log and add it to the other side, 1 plus the natural log x plus y minus 1. And then what does that look like? Well, z equals the 1 plus means that it was shifted up by 1 on the z-axis. And then it's basically the natural log function. Well, if you look at in 2 dimensions the natural log function looks like this. So this thing is going to basically be this shape, except in 3 dimensions. So I don't know if I can show you on the with this camera, but it's basically like a piece of paper. If you fold it like that, yeah, sort of like that. It's going to look like that. The camera didn't really like that. I was trying to focus. So x is 1 and y is 1. And then if you make a dotted line over here, it's not going to exist. So back here, it's not going to exist. And then it's basically going to be this shape. So that would look like, so as you get close to this dotted line, it's going to go down to -infinity. So that would look sort of like this. So it's like a piece of paper that got folded down. I don't know that this is the best 3D drawing. It sort of looks like I'm looking at it from the back side. Well, I actually looked at GeoGebra for that one, and it looks like this. So there's the piece of paper, it's bent and it's going down. There's 1 and 1 are right over there. So as it gets close to the 1 and 1, then it's dropping down to infinity. And then this part is just going up like that. So on the homework, they actually give you pictures. You don't have to draw the pictures. You just have to pick which one you think it is. And of course, with the help of GeoGebra, you should be able to do those pretty easy. Have fun. Let me know how it goes.